We will now show how to do a calculation in eMathStudio. We'll do the calculation in the Notes room. Select it here from the Rooms menu with Notes. In the Notes room you can make your own calculations and write any kind of notes that you find that you need to understand things, or just even communicate with your friends and so on. So here in the Notes room you have My Notes. There are only standard notes before, but we will add an own note, and then there are shared notes, and presently there are no shared notes. So we go to My Notes, and then we add a new note, clicking here. And here is the title. Let's call it an example calculation. And here you can add different kinds of elements to the page. For example, you could add a text page. Let's write the task that we have here. Calculate the value of the expression. I hit Ctrl M to get the math field. I take away this math pen, it's not needed. 2 times 3 plus 4 minus 3 times 4, like that. That's the value we want to calculate. And then we can add here a calculation element, clicking here. And to calculate this value, we start by copying the expression from here, Ctrl C, and then we paste it here in the first line, Ctrl V. Hitting return gives us a copy of this expression, which we then can manipulate. So following the rules for precedence operators, we start by calculating the value inside the parentheses. So 3 plus 4, that is 7. And then we explain this. Like that. We explain what we have been doing. Next, we hit return again. And this time we will do the multiplications. 2 times 7, okay, that's 14. 3 times 4, that's 12. And one more return, and the value will then be 2. So we can see that do the subtraction. Okay, we have now calculated that value of 2 times parentheses 3 plus 4 minus 3 times 4 is equal to 2. Why do we write the justifications? Well, doing a calculation is like playing chess. You can only use those calculation steps that are permitted. Like in chess, you're only allowed to move the pieces in the way that are permitted by the rules of chess. And the justification says which rules you have used to create the next expression, so that it's equal to the previous expression. In our calculation, we have only used 2 rules. First of all, the precedence of operations in arithmetic. This means which operation should be calculated first when we have an expression with different operations. And the second rule is that you can always replace a part of an expression with another expression if they have the same value. The result will be a new expression that is equal to the original one. Writing down the justification shows that we know the rules of the game and we know how to apply them. So let's go back to this calculation that we did earlier and change the justification to be more precise. In the first step, we would have the justification that parentheses should be calculated first. That was the precedence of operations. And then the other thing is that 3 plus 4 equals 7. So this means that we can replace the expression 3 plus 4 here with 7 here. And the result is that the original expression is equal to the new expression. The next case, we now have only multiplication and subtraction. So the rule here is that multiplication should be calculated first, and then we have that 2 times 7 equals 14, and we have that 3 times 4 equals 12. In the last expression, We have only one operation, the subtraction, so we should do that. And we have that 14 minus 12 equals 2. So this means that 14 minus 2 is equal to 2. So that's more precise justifications for our calculations. The first justifications were okay also because it mainly reminded us of which order we should do the operations, and then the implicit understanding that you can always replace part of an expression with another expression if they have the same value. So this is the role of justifications in a calculation. So why should we write down the justifications? Well, first of all, it makes it much easier for the reader to understand the calculation and for the reader to convince himself that the calculation is correct. It's also a great way to explain to students what we do in a calculation when we are teaching a new topic in mathematics. And it makes it easier for the teacher to see how the student has been thinking when the student has written down the justifications. It also makes it easier for yourself to remember how you were thinking when doing this step. This is in particularly useful when you have a more complicated step. You are free to write down the justifications as you want. It can be very short, just a reminder of what you were doing, like we did in the first version of the calculation. You can omit a justification completely, that is, leave the justification empty when it's evident and doesn't need an explanation. A justification can also be long, spanning many lines when it's needed. Essentially, you should choose the level of detail in the justification to fit the intended audience. But in all situations, you should always know yourself why the calculation step is allowed, even if you do not write down the justification. Otherwise, you are just guessing. And that would be similar to cheating in chess, and that will never end well. Next, we will check whether this calculation is correct. We go to the check menu here. There are lots of alternatives, but we will just choose the option check correctness. Click here. And the checker was very fast, so we see that there is a green check mark for each step. And if you click or hover over this check mark, it says that this step has been proved correct by a validity check, and the same for all the others. So this means that this step is correct. In other words, our system, the automatic checker, has proved that 2 times 3 plus 4 minus 3 times 4 is equal to 2 times 7 minus 3 times 4. And the same for the other steps. So each step is correct, and consequently the whole derivation is correct as shown here. So now we have solved the problem, and we have checked that the solution is correct. Next, we will show what happens when there are errors in the calculation. So here we have more or less the same calculations before, but we have added some errors into this calculation. So let's see what happens if we check it. Click check correctness. And we can see that the checker, it says that this derivation was not proved correct. And if we click here on the first line where there's an error, X mark shows there's an error. It says unexpected end of expression. And there's a little red square which says that the computer expected there to be something more. And we can now see that, okay, what's the problem? Well, there is an extra minus sign. So the computer expected there to be an additional value, but there wasn't. So this was just a typo. So let's just remove this typo and then check again. Correctness. And okay, now the first step is correct. The last step is correct. But the second step has a question mark. It says that this step cannot be proved using available checkers. So we'll see what's the problem here. Well, you can see that actually we thought that 2 times 7 is 12. That's not. So let's correct this. So we write this to 14. Okay, so that should take care of this one. Let's check again. Okay, now that step is correct. However, we forgot to correct the last step. So it's not 0 anymore, now it's 2. And then let's check whether this is correct. And now we can see that this derivation is correct. So this shows how to calculate a value for some expression. Let's now talk a little bit more about how the checker works. So the checker goes through a derivation one step at a time and tries to prove each conclusion step and calculation step correct. It creates a mathematical theorem for each such step and sends this step to an automatic theorem prover in the cloud. The automatic theorem prover then tries to find a proof of the theorem. If it finds a proof, then it will say that the step is correct and mark it with a green check symbol. If it does not find a proof, then it marks the step with an orange question mark. The whole derivation is correct if each step in the derivation has been proved correct. The orange question mark does not say that the step is incorrect. It only says that no proof was found for the step. The step could still be correct, but the proof was too difficult for the checker to find. Or then the step is not correct, in which case there is no proof of the step, so the checker will never find a proof of it. It is up to the user to look at each orange check mark and determine whether the step is correct or not. If the user thinks that the step is not correct, then he or she should fix the error in the step. If, on the other hand, the user thinks that the step is correct, then he or she should try to help the checker to find the proof by breaking up the step into smaller and more detailed steps. The checker might be able to prove the smaller step even if it was not able to prove the one big step. You are free to choose the step size that suits the problem. If you are teaching a new topic, then it's good to solve a problem in small steps to make it easy for students to follow each step. If the topic is more familiar, then it's sufficient to show the solution in larger steps and let the students fill in the details as needed. The checker is very reliable in the sense that if it says that the step is correct, then the step is also correct. The steps have been proved with very reliable automatic theorem provers. If the checker is not able to prove a step correct, then that could be for a number of different reasons. First and foremost, the step might not be correct, so there is no proof to find. It is possible that the step is correct, but only under certain assumptions which you have not stated explicitly. So you need to add assumptions there. The step is correct, but the checker ran out of time and/or memory space when trying to find the proof. Or the checker does not have the background theories needed to prove the theorem. The automatic theorem prover uses a number of mechanical theories that describe specific areas of mathematics. There are mechanical theories for arithmetic, for equation solving, for polynomials, for trigonometric and exponential functions, for set theory, for logic, and for differential calculus. This can be used to solve most of the mathematical problems that come up in middle and high school mathematics. There are some areas that are not well covered. For instance, there are mechanized theories for two-dimensional vectors, but presently not for three-dimensional vectors. The support for combinatorics is not that strong, nor the support for probability theory and statistics. There is also no direct support for geometry, although in practice you can get quite far using the algebraic manipulations when solving geometric problems.